too. Okay, chemistry time. Today we are talking about, get out of the way. Perfect. Units and dimensional analysis. You'll remember dimensional analysis by another name, which is unit conversions. But we use those two terms interchangeably, and dimensional analysis is more accurate because we're analyzing the dimensions of objects. But we also want to talk about the units that we use in science. What is the system of units that we use in science? Do you know? You remember? Remember what it's called? It is the metric system. Yeah, it's a revised version of that. We abbreviate the SI, which stands for the International System. Astute observers of the way abbreviations will work will point out that this is actually IS, but in the French it's Système International, which is SI, and that is translated in English to the International System. We call it the SI, and it's kind of like the new metric system, and it's you know the kinds of units that we use. And there are 7 base units. Do you know what the base units are? The unit, we'll say it's abbreviation, and it's what it measures. Yes, mass. Let's start with mass then. There are 7 of these. The one that measures mass, what's the unit?
Kilograms?
It's kilogram, yep. And that's abbreviated capital K, lowercase g. What other base units are there? Let me label this chart. We're going to have it go down to there. Call it the base units, the SI base units. And they're called base units because they form the base of how we measure things in science. They are the bases upon which we build up other units, and we add either prefixes or other units, kind of like you remember in physics how we had a Newton was a kilogram meter per second squared. It's all those units smashed together. Kilogram times meter divided by seconds squared. And so all of those base units squished together formed a Newton. So a Newton is what we call a derived unit. A derived unit, that's not how we make the letter D. A derived unit is one made up of base units. So for example, a Newton is equal to a kilogram meter per second squared, or we might say a kilometer is equal to 1,000 meters. The prefixes you need to know are kilo, meaning, what does kilo mean? You know it. A kilogram is how many grams? 1,000. You got it. Yep. Milli, you need to know, is 1/1000th, and centi, you need to know, and that's 1/100th. There are others. Deci is 1/10th. Giga is a billion. Mega is a million. But these are the prefixes. SI prefixes. SI prefixes. So derived units can either be made of algebraically modified base units or prefix modified base units. What's another base unit? What's another primary property of matter that we use the SI to measure, do you think?
Liter one.
A liter is actually a cubic decimeter. So it's a decimeter, a tenth of a meter, times a decimeter, because volume, remember, volume is length times width times height. And so 1 decimeter, 1/10 of a meter, times 1/10 of a meter, times 1/10 of a meter, those length, width, and height, that makes 1 liter. So nope, not volume. Volume is a derived property of matter. Length times width times height. Actually, in fact, since you cut ahead to that, let's just write it down. Volume equals length times width times height. where V is volume, L is length, W is width, and H is height. In the SI, the base unit for each of these is what? Length, width, and height. All of them, the base unit would be meter. It's meter. It's meter. Meter is the base unit. Centi is a derived unit. This is a prefix. You'll now note that kilogram, how is this a base unit if it has a prefix? And the answer is grams we usually think are too small, and so we determine that kilogram is the base unit, just for that one. But that brings us to the next one, which is a meter, abbreviated M, is the base unit for length. The base unit for length. When we multiply all these together, back into our volume equation, M times M times M, or meter times meter times meter, is just like in algebra. Anytime we multiply something by itself 3 times, we get what? In this case, volume would be measured in meters cubed. Good. So volume is measured in meters cubed. Okay, back to our base units again. What other base units do you think there are? What other very basic properties of matter could we measure? I'm glad you brought that one up too. It is, again, not a base unit. I'm going to erase my derived unit thing here. It is, again, not a base unit, but we do need to talk about it. So we'll just, where rho equals m over v, rho is the Greek letter rho, it's density. M is mass, lowercase m is mass, capital V is volume from above. Density we measure in, well, we'll see in a second, but mass, what's the base unit for mass? Kilograms. The units we use for volume are cubic meters, so density is measured in kilograms per cubic meter. It's a very usual way to measure density. Usually in science, though, we use grams per cubic centimeter, which is identical to grams per milliliter. A milliliter is a cubic centimeter. So nicely, conveniently, and you have pointed out the 2 equations that we need to know for this chapter. Those are them. And it also helps us to understand how derived units work, that the same math that we do to the numbers to find its numerical density, we do that to the units and we get a new density unit, kilogram per cubic meter, for instance, or grams per cubic centimeter. Same thing with volume. When we multiply a length times a height, we don't only get the numerical volume, we also get the unit for volume, which is cubic meters. Okay, what other very basic properties of matter are they? So not volume and not density, those are derived properties of matter. And not just matter, I should say the universe. Some other very basic things we can measure about the universe.
Like speed?
Speed is distance divided by
Time.
Exactly right. And time is one of them. So speed isn't. Speed is a derived property of matter. But time is. And what's the base unit for time? Seconds. Abbreviated S. Sometimes we abbreviate SEC, but the official SI abbreviation is just the letter S. What other basic things about the universe can we measure? I think there's at least one more that I'm pretty sure you can get. Something that we commonly measure in the lab. So we know how to measure these in the lab, but there's another tool that we commonly use to measure things in the lab, especially in chemistry. We didn't do it very much in physics last year because this has way more to do with chemistry. Mass. Weight is the force of gravity acting on the mass of an object. It's one of our lab equipment tools that we use to measure. The easiest one. I mean the easiest lab equipment that everyone already knows coming in. Thermometer. Good. Yeah. What do we measure that? That measures temperature. Yep. And in the SI, we use the Kelvin scale. We do oftentimes in this class we will use Celsius, but Celsius has negative numbers because the 0 point of Celsius is the freezing point of water, and so there are negative numbers. It can get colder indeed than the freezing point of water. So we use Kelvin because there are no negative numbers. Kelvin is just like the Celsius scale in increment, but it starts at 0 as absolute 0. The other three, there's a couple that we don't really use very much called candelas. I think it's CD. Yep. Candelas, which measure luminous intensity or luminosity. How bright something is a basic property of matter. Luminous intensity, sometimes called luminosity. Another one is amperes, which abbreviated capital A, measures electrical, what's the word I'm looking for? Current. And then one we will use this year is the mole, abbreviated almost uselessly MOL, which measures amount of matter. And that's a very, very important one for this class. So this is the one, I would say even of these, this one is kind of the point of chemistry. This allows us to do math with chemistry that we otherwise wouldn't. Of course, these first four are really quite important. In temperature, we use a lot. These other two are really a lot more about things we would use in physics, maybe. In fact, you might remember amperes from physics. But the mole is the basic unit of chemistry that allows us to measure the amount of a substance. Very, very important. So these are the base units, and that should satisfy our objective, which I should have written down, which is describe the use of measurements in science. Describe the use of measurements in science. So I would say, described the use of measurements in science, but now we're going to move on, and this will be the primary focus of most of our lesson, to talk about the specifics of how units are interchanged and how we specifically measure things in science. And so let's talk about that second one first, how things are specifically measured. Your book has a section about scientific notation, which I'm going to trust that you mostly understand from your work in Mr. Snilley's class and math class, but just as a kind of a refresher, if we have something like 1,600,000, what we do to get the scientific notation from that is we multiply the coefficient, 1.6 in this case, times 10 to the, well, how many times is the decimal move? 1, 2, 3, 4, 5, 6. So this is 1.6 times 10 to the 6th. This we call the coefficient. The reason I bring that up is because it is in your book, I think as a vocab word, and it is on the test. This number is called the coefficient, and then that to get scientific notation. You're familiar with this kind of thing, the scientific notation, right? Yeah. On your calculator, as kind of a matter not only of interest but of import to you, is that on your calculator this will show up as 1.6 E6, and that little e means times 10 to the, in this case, 6th. Okay. There's this really neat chart moving on to accuracy and precision. Maybe to demonstrate that I'm moving on, I'm going to erase what we have over here. And I'll change colors too. Accuracy and precision. People get these confused a lot. They're basically vocab words, and so sometimes I will just say, well, you should know them. They're vocab words, but people do get them confused. So I'm going to show you this little chart. Oh, that's probably visible. It's not a chart. It's like a picture, and for you, you can find it on page 47. But it's got this little neat diagram of these targets. So you imagine someone doing target practice in the case of the picture with archery, although I'm sure this would also apply to firearms. But we have the center of the target is what we're aiming for, and depending on how the shots are grouped is how precise it is, and how close they are to the target is how accurate it is. So precision is how similar trial values are to each other. How we might say how tightly grouped our trial values are. And this is one of the reasons we always do multiple trials. Anytime we're measuring time or length or mass or one of our measurements, we want to use multiple trials and average them so that we can see how spread out they are. You might remember from in physical science when we did a lab where we had to time someone running. Well, maybe one of the times was a minute and 3 seconds, maybe the next one was a minute and 10 seconds, and maybe the next one was a minute and 30 seconds. So there's kind of a widespread of data there, and that would tell us that's not very precise data. They're not closely grouped. Whereas accuracy is how close it is to the truth, what actually happened. And how do we determine the truth? Well, sometimes we don't really know that well. But in the case of like your measurement lab that I'm in the middle of grading, there's a known value for the density of zinc or water or whatever. And if you measure that value, you can compare the known value to what you got, and that'll tell you how accurate it is. So accuracy is how true it is, and precision is how tightly grouped the data are. Does that do you have questions about that? Because like I say, people do get confused about that, and I want to make sure that you understand the difference. So again, like on those little targets, the data that is precise, they're all grouped together, but that doesn't necessarily mean they're true. It means they're all grouped together. And then they can also be accurate. They can all be close to the center, but they might not be precise. They might be themselves spread out, but all kind of within the same distance. And of course, we want data that are accurate and precise, that are close to the truth and close to each other. That tells us that we've measured them correctly. Your book goes on to talk about the error calculation, which we did in our lab, but just so that you're aware, percent error equals the absolute value of the found value minus the actual value divided by the actual value. That number times 100%. Will tell you that how wrong you are. And the reason that we use both found and actual values is because the size of the data does really matter here. If we are manufacturing markers and one of our markers is an inch off, that's a lot, right? This marker being an inch longer or shorter would make a big difference. That would not be acceptable, obviously. They wouldn't all fit in the package together. But if we're manufacturing, a cargo ship and the values are an inch off, maybe that's neither here nor there. Maybe the inch is a little bit compared to the actual value that is necessary. So we work with percent error as a factor of both what we did and the truth, so that we can get a quantity that is dependent on both, is what we do with error. Okay, and then the switching gears a little bit, the primary thing that we're concerned about mathematically in this chapter is to be able to successfully complete unit conversion. So this is something that you personally, Tatum, have been doing for, you did it last year and you did it when you were in physical science, so that's 3 years of it. But I'm going to highlight it again for people who may watch this video in the next class who don't know, and just to refresh your memory. So we have really three basic kinds of unit conversions that we do. One of them is very basic, and so we might have something like 12 feet, and we're going to convert that to inches. So the first thing we need to do is write down our given, 12 feet. And then we're always going to multiply these, the given by a factor equal to 1. We're not changing the value. We still want it to be equivalent to 12 feet, but we want to find out how many inches that is. So we want to get rid of feet by putting it on the opposite side of the conversion bar. And we want to put our unit that we're going to on the same side as where we wanted to end up. And then the factors or the values that go into this conversion factor have to be equal to each other, because we're basically multiplying by 1, right? We don't want to change the value. We want to multiply it by effectively 1 so the value doesn't change. So we say to ourselves, self, in 1 foot, there are how many inches? Well, 12. So our answer ends up being 12 feet times 12 inches divided by 1 foot equals 144 inches. You can see that feet algebraically will reduce to 1. We're left with inches as the unit, which is what we wanted. Very simple, right? This one people will be like, well, why do we have to do this at all, right? We could just type in the calculator 12 times 12 and we know there's 144 inches. And while that's true, the claim I always make is if you do this right when it's easy, right? First of all, it didn't take too much time. And if you do it right when it's easy, when it becomes complicated and difficult, you can still do it because you have the process down. So let's do one that's a little bit more complicated and difficult. Let's do one where we'll have to chain it. Let's go from 12 feet to centimeters. Well, again, we write the given, 12 feet. Again, we write conversion factor. We're going to go from feet. Do you know how many centimeters are in a foot? I don't. And so we can't really go from feet to centimeters. Do you see? But we can go from what? Feet to, again, inches. Very good. And then chain another one where we're going from inches to centimeters, because we do know that. And I really encourage you, scientists, to put in the units first. We want our feet to reduce to 1, our inches to reduce to 1. We're going to be left with centimeters, and then we can go back and put our numbers in. In every, again, 1 foot, there are 12 inches. And you have to have this memorized. In every inch, there are 2.54 centimeters. This you should memorize. It will be extremely handy for you to memorize that. Into our calculators, we would type multiply by everything on top, divide by everything on the bottom. 12 times 12 is 144 times 2.54. I'm going to guess it's going to be about 320 something. Let's type it in. So in my calculator, I type 12 times 12 times 2.54. Enter. Excuse me. I pressed the wrong button. 365. 365.76 centimeters is what I come up with. Now, this should probably be more than a side dish, and you'll get some more practice with this, but this is a really important thing for us to bring out. Check out this number. Do you see that? 365.76 centimeters. A lot of times people will ask, should I round this to the nearest tenth? I mean, this is exactly what my calculator spat out, as you can see, but sometimes it'll be, just digits all the way across. So how do you know how many to use? One of the very important things that we do in chemistry, and all the sciences really, is use these things called significant figures. And you should write this down. Significant figures. The point of using significant figures is that we want to have the same level of precision in our answer as we do in the given. We want it to indicate the same level of measurement. So that is to say, if we measured something to be 12 feet, that might be, what if it was 11 feet and 10 inches? Well, if we're only measuring to the nearest foot, we would have rounded that to 12 feet, right? And so then to have this answer of 365.76 centimeters is false precision. It's implying that we measured to the nearest tenth of a millimeter, when in reality, we only measured to the nearest foot. So we want to break this down so they have the same level of significant figures. Here are the rules of significant figures. All non-zero digits are significant. That's the first rule. Number 2, zeros between significant figures, SF, I've abbreviated, are significant. And 3, zeros after SF, a significant figure, and the decimal are, I'm going to underline there, significant. So really the only ones we ever worry about whether they're significant or not are zeros. Let me show it to you this way. If we had, instead of giving the numbers 12 feet, what if it was 0.0000012 feet? Does that change it at all? No, because those zeros are neither between significant figures or after the decimal. But what if it was 12.0000? Do you see how that's different? This shows us, kind of like what we did on our measurement lab, that I measured clear to the 10,000th of a foot and found that it was exactly 12 feet. So that's why those zeros are significant. Oh, and the point of all this, and maybe I'll put this as the 0th rule, is only use the number of significant figures as the least. So if our given only has 2 significant figures, we can only have 2 significant figures in our answer. That's the whole point of doing this. We use the significant figures of the least amount of significant figures. So let's change this back to the way it was. It was just 12 feet. How many significant figures is that? Well, it's just 2. 1, 2. These are non-zero digits. So it's only got 2 sig figs. I sometimes abbreviate a sig fig like a silly person. 2 significant figures. So how many should the answer have? 2. So now we have to round it so it only has 2. So what's this rounded to 2 significant figures? Well, we can't have these at all. So that's 366 rounding it. That's still 3, so it has to be 370. So this answer has the same level of precision as 12 feet. This is telling us we measured to the nearest 10 centimeters. This is telling us we measured to the nearest foot. Those are the same level of precision. And once again, we do this so that we don't get false precision in our answers. We don't want to imply that we measure this very, 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 very precisely when in fact we only measured it to the nearest foot. Let's do another practice one with that. And this time let's have 12.17 feet per second to miles per hour. The division sign in these units is pronounced per. That's when someone says miles per hour, they mean how many miles something has gone in every hour. And this kind of conversion is called a rate. When we have some unit divided by another unit, it's a rate. So the first thing we do again is write our given, 12.17 feet. I'm going to rewrite it as over 1 second. I hope you see how those are the same. 12.17 feet over 1 second. Convert from, for our numerator unit, we're going to convert from feet to miles. And for our denominator unit, we're going to convert from seconds to hours. But check this out. Since seconds is in the denominator, it needs to go in the numerator to eliminate it, seconds to hours. Go back and put in my conversion factors. In every 1 mile, there are 5,280 feet. Should probably memorize that too. And in every 1 hour, there are 3,600 seconds. That's just 60 times 60, right? 60 seconds in a minute, 60 minutes in an hour, 3,600 seconds in an hour. Probably should memorize that too. Answer? Well, handy dandy calculator time. 12.17 divided by 5280, enter, it's important to enter between divisions, times 3600 equals, now you can see that, 8.29, blah, 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 right? Loads of numbers there. How many of those do I use? Well, the rule is only as many as the lowest. We have 4 here, right? 1, 2, 3, 4. 4 significant figures. So I need to round this to 4 sig figs. So it's going to be 8.298. 8.298 what? Well, feet reduced to 1. I'm left with miles in the numerator, hours in the denominator, 8.298 miles per hour. Check to see if that's reasonable. Would it be reasonable if something's moving 12 feet a second-ish to be moving about 8 miles an hour? Yeah, that seems reasonable to me. So we went through, this was a lot of stuff. The main math things to remember are, this we'll be using all year. Significant figures all year long. Every single time we use math, we're going to be using significant figures. You'll get better at it. Conversions should be reviewed to everyone, and we will be using them all year, so you'll get more chances to get good. Rates, chains, basic. And then the equations for you to memorize should be reviewed too, density and volume. Do you have questions about anything? Well, then that's the end. Bye.